Good afternoon, everyone. I am Harshita Bhatia, student of the NorthCap University, Gurugram, and I'll be your moderator for today's webinar on the topic Remote Sensing of Sea Surface Temperature for Ocean Applications. Sea surface temperature is a key climate and weather measurement obtained by satellite microwave radiometers, infrared radiometers, in situ mode, and drifting buoys and ships of opportunity. Thus, with utmost pleasure, I would like to introduce our speaker, Dr. Swapna. She is a life member of Indian Society of Remote Sensing. She is currently working on understanding coastal ocean processes, satellite retrieval, and algorithm development for physical ocean parameters. Ma'am, it's an absolute pleasure to have you here with us. Thank you to all the attendees for joining us today. We will be running a live Q&A session at the end of the webinar. So if you have any queries, just drop them in the comment section and we will take it up towards the end. For the feedback form, you will get the link in the description box below. So without any further delay, let's start. Over to you, ma'am.
Thank you so much, Harshita. That's your kind words. Uh, shall I start sharing my screen?
Yes, ma'am.
Is it visible?
Yes, ma'am, it's visible.
Yeah. Shall I start my talk?
Yes, ma'am.
Yeah. Very good afternoon to everyone. My name is Swapna. I'm working as a scientist in National Remote Sensing Center of ISRO, working in Physical Oceanography Division of Earth and Climate Science area. Today I'm going to talk on remote sensing of sea surface temperature for oceanic applications. The contents of my topic are what is SST, why we need to study, and how this SST is measured, and what are the different types of SST, and how satellite measures sea surface temperature, what is the physical basics of the sea surface temperature retrieval, and different SST algorithms, and few of the ocean applications I am going to talk on. Uh, Actually, what is SST? Generally, in oceanographic family, SST is the water temperature close to the ocean surface. The exact meaning of surface varies according to the measurement method that we are going to talk on different types of SST. Then comes to why to study the SST. We all know that ocean covers almost 75% of the Earth's surface, so it communicates with the atmosphere and in the exchange of energies like heat fluxes, masses, air-sea interaction, and moisture. All these things exchange between atmosphere and ocean, and it has a large influence on climate and weather. So it is called as one of the essential climate variable. Not only that, the upper 3 meters layers of ocean surface has the same amount of heat capacity as the entire overlying atmosphere has. So it is a great storehouse of heat. Not only that, this SST is increase in SST ocean warming leads to the sea level rise and continental ice melting and deoxygenation in the ocean, which are very problematic to the marine organism. Not only that, many numerical weather modelings and prediction algorithms, mesoscale analysis, study of marine ecosystem, all that depends on SST, sea surface temperature. That's why we need to study the sea surface temperature. These are some of the important aspects. And coming to the spatial distribution of sea surface temperature over global ocean, we know that at the equatorial region, sea surface temperatures are high. The average sea surface temperature of ocean is about 17 degrees centigrade and gradually decreases from the equator towards poles. SST varies from about 1.8 degrees minus 1.8 degrees centigrades near the polar CS to about 30 degrees centigrades near the equator. The average SST at the equator is 27 degrees centigrade, whereas the average SST at the 20 degrees latitude is 22 degrees centigrade. At the latitude of 40 degrees, the sea surface temperature average is 14 degrees centigrade, and the rate of decrease of temperature with a increasing latitude is generally 0.5 degree centigrade per the latitude. And we can observe clearly that the southern hemisphere, these are the contours of sea surface temperatures, isothermal contours. So we can see they are very much parallel in the southern hemisphere, whereas in the northern hemisphere they are not parallel because the most of the area is covered by land. The unequal distribution of this SST is due to the unequal distribution of land and ocean masses. That is one of the reason. Not only that, the average annual solar radiation received at the equatorial region and tropical region is surplus in amount, whereas when it comes to the polar regions it is less. So due to this also the sea surface temperature distribution is different at equatorial and polar regions. And this comes to the average global sea surface temperature since 1880 to 2015. If we see this graph, uh, till 1940s, the average global sea surface temperature is below zero, whereas it increased slightly at the 1940 to 1950 years. Again, it dropped down, and again it started increase at the 1980. It started increasing, and it is reaching. It reached in 2016 to the at almost 1 degree centigrade per year. What IPCC, like Intergovernmental Panel on Climate Change, says that over and averagely 0.13 degree centigrade per decade has increased over the last 100 years. And it also 2013 IPCC report says that in next 2000 in next in 80 years it is going to increase 1 to 4 degrees centigrade per decade. So this is a huge change. This is a like increase in temperatures nothing but global warming, sea level rise, and all those are impacted heavily. So coming to how ocean temperature is measured, we know that generally if we get any fever and we need to see thermometers, right? So in the same sense, ocean temperature we need to sense. So for this, in earlier initial days, they used to um, measure the sea surface temperature using the bucket sampling method. Like they collect the sample in the bucket and they used to measure the temperature. Later, scientists employed buoys. This is the buoy. Buoy image in the oceans. So it has the ocean physical parameter sensor like sea surface temperature, pressure, wind speed, winds, currents. All those sensor will be available with the buoys. So this is one such ship SST observations or the global ocean image. Whereas come to the buoy SST, we have a no Rama buoys, Triton buoys. All these are distributed all over the global ocean. But what is the drawback here? In situ measurement come every time. In situ measurements are limited in space, and we cannot see the spatial distribution is very limited, and they are of time means we cannot daily we cannot monitor these in situ measurements. Here comes the solution, the satellite remote sensing of SST. Why satellite remote sensing? Like just now we saw ships and buoys they measure, but they are point location. They cannot give the spatial distribution of the sea surface temperature. But if you see through the satellite, they can cover satellite can cover vast area, and the wider area can be covered quickly, and we can sample them in uniform sampling, and we can monitor daily monthly, in frequent times we can monitor, because oceans are not accessible like if we take in situ measurements every time, and ship time is also expensive, and only through shipping routes only we can means planned routes only we can measure. But in case of satellite this is not the case, we can see the whole area in one stretch. So in this remote sensing, two types of remote sensing are there: passive remote sensing and active. We know that passive is the sensor measures the naturally emitted radiation, and that in this passive remote sensing. Active means this sensor sends the signals towards the earth and it measures the reflected energy received at the sensor. So in this passive remote sensing of SST, we had two types of SST measurements: thermal infrared and microwave. In thermal infrared band is from 3.7 to 10 micrometer region. We call it as thermal infrared, and this has advantage of long heritage. Like since 40 years, we have the SST observations through the satellites, and it has good resolution and accuracy. The thermal emission has its peak in the in thermal infrared peaks in the 9.66 micrometers. So this channel is used to retrieve the sea surface temperature. That's why it has a good resolution and accuracy. But it has also limitation, like it whenever the clouds are there, it cannot penetrate through the clouds, so it obscured by clouds, and we need to do atmospheric corrections to retrieve the better SST. And comes to the microwave SST, here the strengths are mostly, clouds are mostly transparent and insensitive to atmospheric effects, but it has limitation that poor resolution and accuracy, and poor resolution and accuracy, sensitive to surface roughness and precipitation. This is because the low energy received in the microwave signal. See, if you see this, if you see this image, this the above one is the AVHRR infrared SST, and down one is the EMI microwave SST picture. See, in the above image, we can see the clouds as white patches as clouds. So these are all white colored gaps and nothing but clouds. So here we cannot measure the SST. When comes to the microwave SST, see, we have full coverage. There are no gaps. So here is the advantage of microwave, but it has a poorer resolution, like 25 kilometers. But whereas infrared SST has 4 kilometers, 1 kilometers, we can retrieve the sea surface temperature. Just now I told that we have different types of SST according to the measurement depths. So here comes the different types of SST, like 5 SSTs. One is interface SST, that is at the exact air sea interface, which is generally not possible to measure. So generally we only talk about the below SSTs, like skin SST, subskin SST, depth or bulk SST, or foundation SST. Skin SST is the temperature measured by the infrared radiometer at 10 micrometer depth. That is, the satellite infrared sensors can measure the skin SST, whereas microwave sensors can measure the subskin SST. It is the at few millimeters depth, like 2 to 5 millimeters depth, it can penetrate microwave signal. So this is subskin SST. And next, coming to the bulk SST, it is the temperature measured by the buoys at a depth of 1 meters, 2 meters, or 5 meters. Means these are all bulk SST, and it depends on the depth, like 1 meter bulk SST, 5 meters bulk SST. And next, last, come to the foundation SST. It is the temperature of the water column free from the diurnal variability, like it has no effects from the above these things. So if you see this, just now I told infrared if infrared signals can penetrate up to 10 micrometers. So if you see this absorption emission radiation in the ocean skin layer, so microwaves can penetrate up to 5 millimeters depth, whereas infrared are 10 micrometers to 20 micrometers. So visible has, we know that it is a longer penetration of depth. So, and this is the illustration of the skin and bulk SSTs. See, if you see generally in the night times with any strong winds are present, the differences are very less. Like this is the interface SST and red one is the skin SST and this is the foundation SST. So if you see, always the skin SST is cooler in during day and night times, but in the daytime due to the presence of sun, absorption of solar radiation makes the skin layer hot. So that's why we can see this difference. This is nothing, this is the SST minus foundation difference. So see here, still the skin SST is cooler than the microwave subskin SST, and here at the depth of 1 meter 2 meters both are somewhat different, and at the foundation temperature both are equal. So generally, this skin and bulk SST difference results from the absorption of insolation in the first few meters. Just now I told, in the daytimes due to the solar energy, it mostly absorbs the solar radiation and heats up the upper layers of the ocean. And heat loss, in the same way, heat loss due to the sensible and latent heat flux, net long wave rate radiations. These are the causes for the cooling of the ocean. So always the cool skin layer is always present. That's why every time this is low in comparison with the subskin SST. And not only that, wind speed and net heat fluxes have also strong influence on the skin and bulk SST differences. So coming to the physical basis, how we can measure the sea surface temperature using satellite remote sensing. We know that Planck radiation law, all surfaces emit radiation, the strength of which depends on the surface temperature. The higher the temperature, the greater is the radiant energy. So this is the Planck's law. This is the Planck's radiation curve. So at a 300 Kelvin's temperature of Earth temperature, the radiation peak is occurring at around 9.66 micrometers. So this is the infrared window. So that's why we use infrared 3 micrometers to 10 micrometers window to measure the infrared SST. So maximum, so to know at which wavelength we can get the maximum energy, so we use the Wien's displacement law. Maximum wavelength of the emitted energy can be estimated by using this. So as I told, this Earth emission peaks at 9.66 window. So thermal satellite remote sensing uses this window of 3.5 to 4.5 and 9 to 11 micrometer wavelength ranges. Because even though this whole region is we can consider, but it has also atmospheric effects. Just now just now I told. So due to those reasons, we can with these two windows we are using for satellite retrieval of SST. So to select which channels are good to retrieve SST, we have to always select which channels are transparent. Like atmosphere has many components, water vapor, oxygen, ozone, all these aerosols, all these are affecting the sea surface temperature retrieval. So, so in which wavelength bands the channels are transparent, that we have to select. So and one more advantage of thermal measurements is we can observe them in day and night time. So but in daytime, I told that 3 to 4 micrometers and 9 to 11 micrometers window I told. So in these two windows, this 3.9 micrometer band has the problem with solar reflected energy and scattering. So this is dominant in this wave band. So during daytime, if we want to consider this channel, we have to correct this for the solar reflection. But in case of night, this sun is absent in the night time. So this even so it is better to use 3.9 micrometer band in the night time to retrieve the better SST. So during the daytime, if we want to use, we have to correct this reflected and scattered solar radiation in the daytime. Then only we can use this. So not only that, The main concerns in the atmosphere is the water vapor, which is very variable and in time and space. So we have to correct for this water vapor also. So generally, what sensor measures is not the exact sea surface temperature; it is the brightness temperature. Brightness temperature is nothing but the radiation temperature of the black body, which would emit the measured radiance. The measured brightness temperature differs from the actual true temperature of the sea surface because of the non-unit emissivity of the sea surface and intervening atmosphere. So for infrared radiation, the emissivity of sea surface is between 0.98 to zero point 0.9. For microwave radiation, the emissivity of sea surface is 0.4. Just in previous slides, I was telling microwave SST has a poor resolution because of this only. It has less emissivity, so the accuracy of the retrievals is very poor. Like the spatial resolution is also very poor, like 25 kilometers. But in the infrared radiation, the emissivity it is 0.98 to 99, so it has a good emissivity, so we can have higher resolutions in the infrared SST retrievals. So this is the schematic showing the top of the atmosphere radiation at the satellite sensor level. See that the top of the atmosphere radiance received is the combination of surface emission, atmospheric upwelling, and reflected downwelling radiance, which are all functions of frequency. So if we assume the clear sky condition and neglecting the scattering phenomena, the measured using the radiate transfer equation for infrared microwave SST retrievals becomes this. If we expand this each term, it becomes like this. So in this, E is emissivity, T is transmittivity, and Ts is the surface temperature, T bar is the vertical average of tropospheric temperature, and Tb is the brightness temperature, and these are the extraterrestrial brightness temperature and the from the sun also. So each term, if we see in this, emissivity we know. So the unknown terms are sea surface temperature, vertical average of tropospheric temperature, and transmittance. Generally, the transmittance in the atmosphere is depends on the atmospheric constituents. Like major is the water vapor. Water vapor. So this is from these radiative transfer equations and retrieval algorithm, it is understood that if we measure the sea surface temperature in the two channels, the temperature SST will be same, but due to the wavelength band, they have different atmospheric absorptions of water vapor. So if we subtract these two brightness temperatures from the two channels, we can correct this for the water vapor. So that's how we are correcting the atmosphere effects in the sea surface retrievals. So these are the current some of the few of the spaceborne satellite sensors for SST retrieval. And longest satellite SST record is since 1981 from AVHRR. So their sensors and satellite from the satellites, and coming to the ISRO INSAT 3D, INSAT 3D have the images. They have the they are giving the 4 kilometers spatial resolution SST. Accuracies are 0.5, less than 0.5. So coming to the sea surface temperature retrieval algorithms, just now we have discussed we use mid-infrared windows of 3.7 to 4 and 10 to 12 micrometers window. So yeah, depending on the usage of the wavelength bands, we call them as dual window, split window, and multiple dual window and split window. So here we the multi-channel SST is nothing but just now I told this difference between the two brightness temperatures is considered as doing the water vapor corrections in the retrieval algorithm. So the brightness temperature measured is the function of sea surface temperature, geometric coefficients, and uh, this regression, a local zenith angle of the surface and regression coefficient. See here, A0, A1, A2, these are all the regression coefficient which are derived using the regression using the atmosphere in situ measurements of sea surface temperature. Whereas this T4, T11, T12, these are the brightness temperatures measured using the different channels like 4 micrometer band, 11 micrometer, 12 micrometer band. So the difference between these two channels is used to correct the water vapor correction. So this is how retrieval algorithm of SST is there. And coming to the nonlinear SST algorithm, see sometimes the measured brightness temperatures are above the reference level. To keep them in the reference levels of the global ocean temperature, so a first guess SST is introduced in the second third term, that is first guess SST in kelvins is introduced. This is the reason for the non-linearity in the this equation. So that's why it is called non-linear sea surface temperature. So this first guess SST and these are 12, 11 and 12 are brightness temperatures in that these wavelength bands, and theta is the local zenith angle at the surface, and these are all regression coefficients. And coming to the ISRO INSAT 3D SST retrieval algorithm. INSAT 3D is an advanced weather satellite of India for meteorological and weather observations to monitor on a regular scale. It is a geostationary satellite, so we can monitor in a half an hour interval. With the advent of INSAT 3D are also launched. So with two through two satellites, now it is a temporal resolution is very high, like every 15 minutes we can see the entire image of Indian Ocean. So this INSAT 3D uses the split window thermal window channels of 10.2 to 11.3 micrometers during the daytime, and mid infrared window is used only night times. Just now in the previous slide we have seen it has the effect of solar reflection and scattering in mid infrared during daytime. So we always use this channel in the night times for a better retrieval of the SST. So these are and the advantage of this INSAT 3D SST is this is a geostationary satellite, so we have high frequency in terms of times. So every half an hour, every 15 minutes we have the sea surface temperature observation, so which are helpful in diurnal variation study of sea surface temperatures. So this is also the equation is similar in the previous algorithms. These are the some of the important parameters of each SST during day and night time. So this is the pictures of INSAT 3D SST. See, it zero means in a day I took 4 images. So how the full Indian Ocean is covered. See these white. Just now we saw that infrared has the cloud. Clouds are the problem in the infrared SST. So these all white gaps are due to the clouds. So whenever clouds are present, we can't retrieve the SST. So that's why we need to correct for the clouds and atmospheric water vapor effect. See, next coming to the mode is SST retrieval algorithm. It uses the nonlinear SST algorithm. Just now we talked about. See this surface is the climatological estimate it uses instead of first guess SST in the third term, and this equation is similar in the previous form. So whereas T11, T12 are the brightness temperature channel measured in the channels at 11 and 12 micrometers, and this is a climatological SST in that area, and theta and all are satellite zenith angles. So generally, the operational implementation of SST follows these steps. First, the received radiance at the sensor level is converted to the temperature using the inverse Planck law. These lookup tables are prepared before after the sensor calibration. So now I receive this much of radiance. It is the temperature equal to this much temperature. So they prepare all that lookup tables after the calibration of the sensor. Then discrimination between the radiance and clouds. See, in the infrared, major problem is the clouds and atmospheric reduction. So to differentiate the clouds, we use some of the methods like thresholding methods or spatial coherency test, or in fact we can use visible bands in which solar clouds has higher reflectance. So those whenever higher reflectance clouds are present in the other channels, combination of the channels with this infrared channels, if we use, whenever the cloud is there in that channel, due to the high reflectivity, that pixel automatically we can omit or remove from this infrared channels. So that is also useful for cloud screening. And coming to the atmospheric correction, the major constituent we were talking about water vapor. So by subtracting the two channels brightness temperature, we are correcting the water vapor corrections. See, we were talking about 3 micrometers and 11 and 12 micrometers channels. So in this, water vapor absorption is more in the 12 micrometers. That's why in all algorithms, if we see, this here the water vapor absorption is more, so hence the brightness temperature will be always less. So comparatively this is medium, and brightness temperature of T4 is very means very high comparatively. That's why we subtract from the higher value to lower value. Then after the atmospheric correction, we compute the sea surface temperature, and this is the general operation implementation of the SST. See, coming to the, this is the just now we talked about the what is SST and why it is important, and what how to measure the SST and different types of SST, and what are the retrieval algorithms using satellites, and different cloud corrections and water vapor corrections using in the retrieval algorithm we discussed. Now coming to the ocean application, SST has vast number of application, but due to the time I am limiting to the few of the application which I am touching upon in this. Like SST SST images can be used. Why this SST we all can observe these things means, by measuring the SST from the satellite, these all phenomena are represented in that SST image. How we just in the next slide we are saying, like I am going to talk about fronts, upwelling, AC exchange, and potential fishing zone, thermal fronts, and coral bleaching, and it has numerous applications, but I'm sticking to these things. See, if you see, SST patterns are visualized in every spatial pattern, like fronts, jets, eddies, upwelling, equatorial planetary waves, low Crosby waves. These are all visible in the images captured. See, if you see these are the fronts. Fronts are the thermal fronts are nothing but the water masses of different temperatures. See, here the temperature is different. Here the scale I forgot to keep. See, this is of different temperature, this is of different temperature. So here a thermal front has formed here. And not only that, upwelling is nothing but the vertical movement of the cooler water, cold water to the surface, so which brings the nutrients to the surface, which are important for the fishing and all marine organisms over the surface. So if you see this image, it has lower temperatures compared to this area. So it is using the satellite image only, we can say this is the upwelling area. See, all these phenomena like fronts, upwelling, all these currents, thermal fronts, all these are visible in the satellite imagery, which we can analyze. Not only that, it is used for operationally weather forecasting, ship routing, fish finding, and climate variability prediction also. See, this is the most favorite example like the SST image of Gulf streams. If you see, observe, see that temperatures are clearly visible. These are the warm current in the Gulf Stream present. So we can see the meandering effect, eddies forming. All these are we can identify these features using sea surface temperature images. See, these are all cold waters. These are the high warm waters in the Gulf streams. See, by just visualizing the image, we can identify these are the patterns observed. These are the meandering of these warm water eddies are forming in this area. So we can study. We can easily identify using the ocean features like fronts, warm currents, uh, upwelling regions using the satellite SST. Coming to the AC exchange, we all know that the major driving forces of surface flux of heat, freshwater, momentum, wind state drive variability in the ocean state. See, all these are key variable to measure this long wave radiation, latent, sensible, short wave radiation flux. All these are important to compute the heat balance of the heat content of the ocean. See, for all these terms, SST is the a requirement to calculate the sensible heat, latent, short wave, long wave. These all parameters depends on the sea surface temperatures. So to estimate the heat content of the ocean, we net heat flux, all these required. SST is the primary parameter and key variable in this heat budget studies. And just now I was talking about thermal front. This is a work carried out at NRSC by us. Like just now I told thermal fronts are nothing but the uh, uh, different water masses of different temperature in the adjacent region. So generally the thermal fronts are associated with a high productivity because they trap the nutrients in that region and which are favorable for the fishing and all those things. So they have high productivity and they act as a boundary where nutrients, zooplankton and phytoplankton get trapped along the boundaries and thus increase the productivity along the front. This study we carried out using the Moody's daily SST data, and these are using the Cayula Cornelon method. We identified these thermal fronts, and here these are the maps of thermal front climatology maps of the Arabian Sea and Bay of Bengal region, Northern Bay of Bengal region. See here the most of the thermal sun fronts have formed. These are the percentage of the thermal front density. See here the around 36% of thermal front means on a weekly time scale we carried out this study. So 36 percentage of thermal fronts are present in this area. So they are trapping. An interesting finding is that they mostly trapped between 10 to 50 meters bathymetry range. So they are trapping the nutrients within this. We have also studied that most of the fishermen goes to this place only and catches the fish. See, means this is the potential fishing zones also identified using the sea surface temperature data. That's next slide I'm going to show you. See, this is a potential fishing zones. See, using a SST image and combined with chlorophyll, combining both these two, we can give the advisory of potential fishing zones. See, low SSTs and high chlorophyll content are the better proxy for potential fishing zone. So this study has been carried out in NRSC Hyderabad and during 96 to 97 using AVHR SST data. Now it is operationalized with inquires as PFZ advisory. And next coming to the coral bleaching. See, corals like they are to coral bleaching. There are many reasons, but the major cause is the temperature, the thermal stress, which causes the mass of coral bleaching, mass coral bleaching, and the mortality of the corals. See, if the thermal stressing is nothing but if it is the temperatures, high temperatures are persisted for the long time, like few weeks. So that is becomes a thermal stress to that corals. So the thermal stress, if it is persistent throughout the weeks, like 1 weeks to 4 weeks, 5 weeks, so the thermal stress builds up there. So to identify the coral bleaching, the threshold is set like bleaching threshold is the maximum monthly mean plus 1 degree centigrade is set as a uh, threshold level. And if it is above this threshold level, it is the thermal stress in that region. Not only the temperature, generally if the temperature is 28.5 degrees centigrade above, generally we observe for this bleaching threshold, means not only temperature should be excess about 28.5, but the degree heating weeks, like if the temperature of 28, suppose it is persisted for 1 week, there is no 0 weeks, no thermal rise. But if it is persistent for more than 4 weeks, though, so it is leading to thermal stress and significant bleaching. If the temperature is so high and it is more than 8 weeks, means the thermal stress is leading to a widespread of bleaching and significant mortality. So like this, sea surface temperature is is the input to identify the coral bleaching areas and hotspots of the, this is the hotspot regions of coral bleaching, um, by sourced by NOAA. So here also the major cause is the temperature of the ocean. So if it exceeds the certain threshold level, it is going to bleach the corals, and mass coral bleaching and mortality will happen. So these are some of the few applications of sea surface temperature. Uh, Not only this, there are many numerical method modelings, ocean models. All these use the sea surface temperature as their input. So it has vast amount of applications, like coastal applications, open ocean application. Many are there. So with these few application, I am concluding. Thank you so much. Hello.
Glad to have you here today. Thank you, ma'am, for such a breathtaking session packed with massive knowledge and value. Well, with that, we are open to Q&A session. Can we have the first question on the screen, please?
And first of all, I would like to thank the NorthCap University for this opportunity uh, to interact with you people, and I am glad to be part of this event. Thank you so much.
Thank you, ma'am, for taking out your precious time to broaden our knowledge. Thank you to all the attendees for joining us today. We hope to see you all soon in our upcoming webinars. Till then, stay safe and stay tuned.
Thank you.
Thank you, ma'am.